Alright, so I'm going to discuss image compression with the discrete cosine transform. And so to motivate, consider having a color picture that measures 3 by 5 inches. So we have a color picture that is 3 by 5 inches at a resolution of 400 dots per inch. Okay, so 400 dpi. So the image is 15 square inches. Each square inch has 400 times 400 dots or pixels. So it has 160K dots or pixels. Okay. So with 15 square inches, 160,000 dots per square inch, we have a total of 2,400,000 dots. And if each dot requires 3 bytes of storage, we require a total of about 7 megabytes of storage. And if you think about your files that you have on your P drive, wherever you have them, I mean 7 megabytes is a pretty big file, and so this is something that we would have to compress. And so now I'll get into the details of how to compress an image. So now I'm going to give an example of what's called lossy compression, which basically means that in compressing this data, we're losing something. Okay, we're not quite going to be able to recover the exact image. Okay, and basically lossy compression is a more applicable way of saying we're going to do a low pass filtering. Okay, we're going to have an image, we're going to consider a grayscale image that is given by this 8 by 8 matrix. And then we are going to apply a transform and then sort of delete some of the entries. Okay. So we're going to consider a grayscale image where the numbering goes like this. 0 corresponds to black, and 255 corresponds to white. And so we have our shades of gray between 0 and 255. And so imagine each pixel of this image being represented by an 8 by 8 matrix. And so I'm going to give a matrix. I'm not going to give all of the entries of a matrix. I mean, you could imagine that these entries are all between 0 and 255. So put a 33 in this first row, first column, 41, and all the way down to 42 here. Okay, 33, and then 29 in the first row, all the way to an 8. 31 in the 2-2 entry down to, and so this last 2x2 in the bottom right corner will be 129, 136, and 49 and 55. So whatever the entries are in between, they're all between 0 and 255. Now we're going to perform an operation where we, it's called a level shifting. And this is to get the entries to range between minus 128 and 127 instead of 0 and 255. And to do that, we're going to subtract 128 from all of the entries. Okay, this is to, as I said, we're going from the entries ranging between 0 and 255 to a range between minus 128 and 127. So the entries are in the interval from minus 128 to 127. All right, now I'm not going to write down what this new matrix is. Okay, what I will write down is that if we do this level shifting and we compute the discrete cosine transform, we get that y, which equals Cx C transpose, okay, where C has been given in previous lectures. The matrix Y looks like the following. So here I'm going to write in a few more than I have previously. A few more of the entries. So we have minus 283, minus 369, minus 23, leading to a 5. Down the first column, or let's see, let's put minus 92 here, minus 340 here, and 11 here. And so now if we go down to other parts of the matrix, there's a 9 down here, and in the bottom right corner we have an entry of a 2 here, 0, 0, 3, minus 2, minus 2, minus 1, 1, 1, and 0. So what you should notice from these values that you're seeing here are that the magnitudes of these entries are larger in the top left, and they go down as we move from the top left to the bottom right. Okay. And so now, if you think of these entries as weights of the interpolant that we get from the discrete cosine transform, it's clear that the weights are heavier for the lower frequency basis functions, and they are certainly less for the higher frequency basis functions. So what can we do because of this? Well, we can, a simple thing to do would be to basically just enter zeros for the entries in the bottom right. For example, we can keep entries such that I plus j is less than or equal to 8. And we'll set all other entries equal to 0. And so what do we get if we do this? So I'll call this y bar. Y bar equals the matrix. We keep the minus 283. We keep the minus 369. We keep the entry in the second to last column, which is a 1, but the last entry of the first row is a 0. And so we have, continuing, we have a minus 92 here that we keep. We go down to the second to last row where there's a 1 here, 0 in the last row, and so we have zeros basically along this diagonal that runs from bottom left to top right. Zeros here and non-zeros in the upper part. So what we've done here is a crude form of compression. Certainly there can be ways of improving on this, and that's what we'll do that's what we'll do next. I'll introduce the concept of quantization. Okay, so this quantization, what it's going to do, it's basically going to rescale the coefficients of the lower frequency terms that are in the top left, which will require fewer bits of storage. Okay, and this is of course in addition to zeroing the coefficients that are in the bottom right, and those are ones that correspond to the higher frequency terms. Okay, so this quantization goes like this. What we want to do is we want to divide each of the entries in our matrix Y by various numbers. And so it's the quantized matrix looks like this. So we have a Y sub Q where we perform this quantization is being performed on Y, which looks like it is a rounding of each of the entries in Y by the entries in Q. And this rounding occurs entry-wise. Okay, and so an example of a matrix Q would look like something like this. And this is so let me just point out that Q is called the quantization matrix. And an example of a quantization matrix would look something like this. Q sub K L might look something like this. 8 times S times K plus L plus 1, where S is some parameter. In the example we're going to look at, we're going to set S equal to 1. And K and L range between 0 and 7. Of course, K and L are just the indices for rows and columns. So in an explicit form, Q is going to look like, if we, for this particular example, Q looks like this. So we have S times the following 8 by 8 matrix. So we have an 8, 16, 24. You hopefully see the pattern until we get to a 64 here. 16, 24 down the first column. We get to a 64 here. And there's a 24 here. And if we continue in this fashion, we can fill in the rest of the matrix. I'm just going to put in a few more terms down here. Okay, so this is the quantization matrix for this particular example. Our second example is the one that we'll actually use, and this second example is called it refers to Luminance quantization. Okay, and Luminance quantization is basically a JPEG standard that's been developed throughout the years. It's based on what's called psychovisual thresholding. And the Q matrix, our quantization matrix, looks like the following. And I won't write in all of the entries, but it's not quite like our previous Q. Again, I'm using the one reference that I showed you guys in class the other day, and I'm just going to write in a few of the terms, not all of them. And you'll see the general idea is that the entries in the top left are smaller than the entries in the bottom right. And the reason is the following. Basically, we want to try to zero out the entries that are in the bottom right. Okay, and that's why the entries in the bottom right of Q are large. We also want to rescale the entries that are in the top left. Okay, so we are dividing by something. It's just much smaller, so that we're not going to ultimately zero them out as well. Okay, so just to list a few more of the entries in Q. And so you can see that in this bottom right, we have entries that are larger than the top left. Okay, this should be enough to illustrate what we have here. So now, if we actually apply this quantization to our matrix Y that we computed, which is the discrete cosine transform of our matrix X, and that was our matrix X that was shifted by 128, we get the following matrix. So if we apply this quantization to Y, we get a matrix that looks like this. And here I'm going to write in all of the non-zero entries, and all other entries will be 0. Okay, so you can see that where we have non-zero entries, they're all towards the top and the left. And so as you can see in our quantized matrix Y sub Q, more zeros were obtained than if we simply just zeroed out the entries such that I plus j was greater than 8, greater than or equal to 8. And we also have the non-zero entries that are smaller in magnitude, and these require fewer bits in order to be stored.